Hello, this is Mrs. Pinkerton, and this is 2.7 VSEPR and bond hybridization, the last topic in Unit 2. This topic is a lot of memorization, so there's really no getting around that, and I would recommend using a Quizlet or index cards or something to help you memorize this, but it is covered on the AP test, and it's something you should memorize. So valence shell electron pair repulsion theory is what VSEPR stands for, and it's used to predict the geometries of molecules and polyatomic ions. These geometries are the result of electrons in lone pairs or bonds trying to minimize their electron-electron repulsions by positioning themselves as far apart as possible. So we're looking in a three-dimensional space on this part of the unit, where we're imagining that the attached electrons on the central atom are trying, or lone pairs are trying to configure themselves so they're as far as possible. These electron domains determine the specific molecular geometry, and that's what you're going to have to memorize, of a molecule. So some molecules are considered nonpolar, and again, these are molecules, so we're talking about covalent bonds, which consist of nonmetals. So even though they consist of polar bonds, they can be nonpolar. This is due to their geometry causing the dipoles to cancel each other out. Remember the rules. Molecules composed of only nonpolar bonds are going to be nonpolar, regardless of the shape. Molecules in which the central atom is symmetrically surrounded by identical atoms are nonpolar, even if the bonds are polar. So this goes back to 2.1 when I was talking about BCl3 being nonpolar, even though in the example we said polar because of the differences in electronegativity, but because of its molecular geometry, it's actually nonpolar, and I mentioned we would discuss this during 2.7, so here we are. All other shapes are asymmetrical, so if they contain any polar bonds, the molecule is polar overall. And lone pair electrons on the central atom can also cause a molecule to be polar. So you have to take into account the lone pair of electrons, and that's why we show them on our Lewis structures, because they're important. So on the AP test, you're going to have to know up to this area here. And then anything below that is not covered on the AP test, but it's still good to know, because especially if you go into a college level chemistry class beyond AP Chem, you will need to know all the different shapes and structures. So what you're going to need to know is the molecular geometry here, and if it's linear, if it's trigonal planar, or if it's angular or bent. And notice the only difference is this is a lone pair of electrons. Tetrahedral, trigonal, pyramidal, angular, or bent again. So you're going to need to know all these structures and what they look like and their names. You're also going to need to know the bond angles that they make, and so we'll write those down as well. So a linear molecule has a bond angle of 180 degrees. So it's basically a straight line. In a trigonal planar, the angle in between those is 120 degrees. If there's a lone pair, the angle between these two atoms, the lone pair repels more. So this is a little bit less than 120 degrees in here. So if it's got a lone pair, it's going to repel it more, so the bond angle is going to be a little bit smaller, and you need to know that. For this, there's 4 items on the central atom, the bond angle is 109.5 degrees. So I'm talking about the angles in here. Now again, if there's a lone pair, it's going to repel this more. And it's actually like 104.5 degrees or something, but you just need to know that it's going to be a little less than 109.5. Okay, so you're not going to need to know the exact angle, but just know that these lone pair cause a greater repulsion. So you're going to have a smaller angle than 109.5, a little bit smaller. So that's what you're going to need to memorize for the AP test and be able to recognize the angles and the shapes, and also if there's lone pairs, that it will make these angles a little bit smaller. Okay. So based on the geometry, this BF3 molecule is nonpolar, and same with this CCl4 molecule, because if you notice, there's no lone pairs, and they're equally pulling on that central atom. So you'll notice if it's like a tug-of-war, they're all pulling, they're the exact same atoms, so the electrons are pulled towards those atoms equally, so they cancel each other out, and we call them nonpolar. Now, if we don't have an equal pull, and the reason why these are polar is because nitrogen actually has lone pair of electrons here. Okay, so they play a part in this, so it's no longer symmetrical. You're looking for asymmetry, either 2 different atoms that have lone pairs on them, such as here, 2 different atoms, or atoms with different molecules with different atoms attached, so they're pulling unequally. So again, you're looking for symmetry when you're looking for nonpolar molecules, okay? And lone pairs do count in that. Two, four, six, sorry, there's only 1 lone pair here. I knew I was drawing too many, okay? So here it says example, what are the bond angles on this molecule? So first thing we're going to see is how many elements are attached to sulfur. I've got 1, 2, 3, 4. So I'm here, number of electron groups are 4, and we also include the atoms. I see that I have 2 lone pairs and 2 fluorines. So I'm here at angular or bent. So you're going to need to know that that's an angular or bent molecule. I know that the bond angle is 109.5, but since I've got these lone pairs here, it's going to make this a little smaller. So I would say less than 109.5 degrees. Okay? And that would be the answer. So you don't need to know the exact angle, which I said was like 104.5, but you would just have to be able to tell the that it's a little bit less, and why, and that's because you have additional repulsion from those lone pairs. Okay, so here's some examples. You're going to identify the molecular geometry of the following molecules, and again, we just count how many electron domains, and then we look at our chart, and again, unfortunately or fortunately, this is what you're going to have to memorize. So I have 1, 2, 3. I have 3 pairs, and then I have 1 lone pair. So if I go to 3 with 1 lone pair, I have a bent or angular geometry here. Let's go to the next one. I have 4 domains. 1, 2, 3, 4. I have an electron pair on top. So that is trigonal pyramidal. Okay, let's go on to the next one. Again, I have four items attached, and then I have 2 atoms on the bottom, and again, you can look at the chart. Let me make this smaller, and this again is bent. because I am here. Okay, now we're past the ones that we have to memorize, but since we have a chart above, we can look. And I have 1, 2, 3, 4, 5, 6 electron domains, and then I have 2 that are lone pairs. So if I look for 2 lone pairs with 6 atoms attached, I'm here. That is square planar. On the next part, it says identify if the following molecules are polar or not or nonpolar based on their molecular geometry. And so again, you're looking for symmetry. Is it symmetrical? And so this one, this BF3, has the same atom attached to it, no lone pairs. So this is symmetrical, it's nonpolar. Again, same for the CF4. This is also nonpolar because same atom attached all around. This one, XEF, I'm going to look at my chart actually. So I'm going to look at my chart up here. And again, this is a bit outside of what you need to know for the AP test. But I have 1, 2, 3, 4, 5. So with 2 atoms. So I go up here, I look at 5. I have 2 atoms. It's linear. It actually does have symmetry. See, those are on one plane and this is on a separate plane. So it actually is a nonpolar molecule. That's a hard one. If you wouldn't have gotten that, that's okay. You wouldn't see something like that. And again, this one is symmetrical, nonpolar. Okay, so those were all nonpolar based off of their symmetries. We're going to talk about hybridization next, and hybridization is the concept of mixing 2 atomic orbitals. So you'll be asked what the bond hybridization is. This is when 2 nonmetals bond, their orbitals form a hybrid. And this gives rise to a new type of hybridized orbital, and the shape of the hybrid orbitals are a mix of the shape of the original atomic orbitals. So you'll see over here, these are the shapes of the original orbitals on the atom, and then when they bond, they make these hybrid orbitals. So these overlapping orbitals result in a sigma or pi bond. In general, the sum of the superscripts on the hybrid orbitals equals the number of electrons domains around the central atom. So we can have hybridizations of, for AP purposes, SP. We can have SP2, and we go up to SP3, and that's the most you'll need to know. And basically what you look for when you're doing bond hybridizations is you're looking to count the number of electron groups around the atom, okay? And each single bond is a group, each double bond is a group, each triple bond is a group, and even lone pairs are a group. So if there's 2 groups is SP. If there's 3 groups, it's SP2. And if there's 4 groups, it's SP3. Okay, so what is the hybridization on methane? Well, I'm going to look, and there's 1, 2, 3, 4 groups around that central atom. So this is going to be an SP3 hybridization. And again, even if this was, say this wasn't here, say this was a lone pair. Again, lone pairs count, 1, 2, 3, 4 groups still attached. That's SP3. Another example is even if this were a double bond, which doesn't make sense, but it's still just 4 groups, it's still SP3. Okay, so you're just counting groups attached to that central atom. Okay. Another example is, say, oxygen and oxygen. We consider that, even though it's just 1, we consider that 2 groups. This would be an SP. Okay, so those you would be asked what the hybridization is around the central atom, and that's how you would determine it. Sigma bonds are always the first bonds between two atoms. So a single bond is a sigma bond. Pi bonds are the second and third bonds resulting from the overlapping of the p orbitals, forming double and triple bonds. Oops, sorry. So you'll see here, this is a single bond. Right here, that's your sigma bond. And then when these are your p orbitals, when they overlap, they form these big pi bonds, okay? So if I have a single bond, I have one sigma bond, okay? If I have a double bond, I have one sigma and one pi bond. And sometimes we just say one sigma, one pi. And if I have a triple bond, I have one sigma bond and I have two pi bonds. And yes, you do need to know that. They will ask you that question. How many sigma, how many pi bonds are in this molecule, okay? So here's an example. In the reaction represented above, what is the hybridization of the C atoms before and after the reaction occurs? So this is asking for the hybridization. So we're up here. Is it sp2, sp3? And we're only looking at the carbons. So notice all the carbons are the same, right? So if I look at just one carbon, I see that there's 1, 2, 3 groups attached to it. And remember that 3 groups is sp2. And again, if you count the superscripts, I have 1, 2, 3 right there, okay? So this is sp2. After, all the carbons are the same again. But now my double bonds have gone and each carbon has 1, 2, 3, 4 groups attached to it. So 4 groups is sp3. And again, you'll notice my superscripts, if say this had a 1, which we don't write, that would add up to 4. So that's another way to check that you did it right.